Okay, hello everyone. Welcome to this month's COFFIES Seminar. It's my great honor to introduce our speaker today. Dr. Marco Stangalini is a senior scientist at the Italian Space Agency, aka ASI, Agenzia Spaziale Italiana. Sorry, I learned from Google Translate. I learned it hard. He earned his PhD in astrophysics from University of Rome Tor Vergata. Prior joining ASA, he held research positions at the Max Planck Institute for Solar System Research in Germany and the National Institute for Astrophysics Astronomical Observatory of Rome. Dr. Stangalini's research spans a broad range of topics in solar physics, with a focus on small-scale solar magnetic fields, wave dynamics in the solar atmosphere, and high-resolution observations. He is also involved in the development of international space missions. He is the ASI project scientist for the Solar Orbiter MATIS instrument and ASI project scientist for the NASA MUSE mission. Today, he will give a talk about his recent work on the dynamics of small-scale magnetic fields modulated by solar cycle. Thank you. Let's welcome Dr. Marco Stangalini again, and I will hand it. You have the Zoom now, Marco.
Thank you very much. Good morning, everyone. Thank you very much for this invitation. I'm very glad to see friends also connected today, and also to present these recent results that we have published recently in ANA. And also, I'm very glad that also to discuss these results with you. As you will see shortly, there are many questions arising from these results, so I'm particularly interested also in discussing possibly this with experts like you. So this is part of a series of works that we are doing. This is an international collaboration. There are many colleagues involved and PhD students. And this is one of a series of works that we are doing, trying to bridge small scales in the solar atmospheres, in the atmosphere with the global scales, so with the typical time scales and spatial scales of the sun. So to start with, let me introduce the focus of this talk. So the small-scale magnetic fields in the solar photosphere. So as you know, when you look at the sun at high resolution, you see a lot of small-scale magnetic elements down to the spatial scale accessible by current high-resolution instrumentation. So down to very small scales of the order of 30, 40 kilometers, which are now resolved by 4-meter crossover telescopes. And these small scale features, which have lifetimes of the order of a few minutes, ranging from a few minutes to several minutes, 30, 40 minutes on average, are affected by the photospheric convection, so by the turbulent convection. And these magnetic fields vertically connect also from the energetic point of view, different layers of the solar atmosphere. So they are very important, are thought to be very important, for example, in the acceleration of the solar wind, and also for the heating of the higher layers of the solar atmosphere. So, so they act as a energy in transferring energy from the base of the photosphere above to the upper layers of the solar atmosphere, and these are this is something that has attracted attention over the last years. And in this magnetic elements, different waves can be excited. So you have the granular buffeting, you have this turbulent convection, continuously exciting waves in these magnetic tubes. So for a cylindrical flux tube, you can excite several types of MHD waves, resonant modes. As in this case, this is a sausage mode, meaning the compression and decompression of the flux tube. But you can also have the kink mode, which is the only one resulting in the displacement of the flux tube itself. But you can also have higher order modes, like in this case, this is a floating mode, and this is another floating mode. This MHD modes can be excited at the same time in these flux tubes, and also they can take part to the energy transfer from the base of the photosphere up to the upper layers of the solar atmosphere. But this can be also directly observed and identified thanks to high resolution observations, as in this case. So this is work published recently by Shaheen Jafarzadeh using solar orbital data, free data. And you can see directly how this is the perimeter of a small scale flux tube. You can see directly different wave modes excited at the same time. So sausage mode with the expansion and the compression of the flux tube, but at the same time a kink mode resulting in the displacement of the flux tube, and a floating mode as well. In this talk, I'm going to focus on the kink modes. So those modes which result in the displacement of the flux tubes, and that you can see in the middle of this panel. And again, this is the only mode producing the displacement of the flux tube itself. And interestingly, this kink mode is actually can be, as in this case, can be found at different layers, different heights in the solar atmosphere. And in this way, the flux tube acts as a wave, so transferring energy to the higher layers. And in this movie, which is made by using a combination of high resolution data, you can clearly see by eye that this kink mode is actually present at different heights in the solar atmosphere. And this movie was made by using ground-based and spaceborne observations at the same time. And you can immediately see this the propagation also of these oscillations, which is also seen in this phase diagram. This is a phase diagram of the kink oscillations between obtained by high resolution observations at two heights, in the photosphere and the chromosphere. And this is the phase lag between the two heights. And you can see here there is a positive phase, and the dashed blue line represents the expected phase lag for the kink modes. And this is well in agreement with the observation, meaning that you have an upward propagating kink mode in the small scale flux tubes. This is just to say how important are this kind of MHD modes also for the energy budget of the entire solar atmosphere, but not only for the energy budget, but also, for example, for the acceleration of the solar wind. So in this talk, I'm going to focus on this particular mode, on the kink mode, and in particular, what I wanted to say or to add also is that you can also find combination. You can also find simultaneously different modes at the same time, and some of them can be also coupled. So there is, as in this case, there is you can also have a particular phase relation between different modes, and this is suggesting that there is a coupling between the different modes. So in this example, you have a coupling of or the horizontal oscillations of the flux tubes, so the kink oscillations, and the longitudinal velocity, Doppler velocity inside the flux tubes, meaning a coupling between the kink modes and the longitudinal modes represented by the longitudinal Doppler velocity oscillations.
Can I
So,
interrupt?
sorry?
James Wang.
Yeah.
How I think solar physicists always talk about Alfvén waves. Are kink modes a species of Alfvén waves, or are they different?
So a kink mode is an incompressible mode, resulting in the displacement of the flux tube.
Oh, is it
In a
compressible?
structured medium, like cylindrical flux tube, the Alfvén mode is a torsional mode. That's the difference.
Okay.
Okay, thank you. So generally, when we investigate the wave dynamics in different magnetic structures in the solar atmosphere, so sunspots, but also small-scale structures with sizes of the order of a few kilometers, we generally concentrate ourselves to the resolving the main periodicities and to solve the main time scales of the single flux tubes or the single sunspots or so on. So we really focus and concentrate our attention to time scales, very short time scales. Okay, so we generally use data sets with a total length of the order ranging from 40 minutes up to 2 hours, 3 hours in our resolution of observations. And this is perfectly fine. This is already enough to fully resolve the main physical processes involved. So, for example, to fully resolve and to fully detect the eigenmodes of these structures, the resonant modes, for which we expect frequencies of the order of a few millions. So we are in the domain of a few with periods of a few minutes, right? So data sets of the order ranging from 40 minutes to 2 hours or 3 hours are already enough to study this and to investigate the wave dynamics in these magnetic structures. But in this series of works, what we want to do is to bridge the gap between these small scales and the global scales of the sun. Because usually when you use data sets with a length of the order of a few minutes, a couple of hours, of course, we are not able to possibly find a coupling between completely different scales. So a coupling between the small scales and the global scales of the sun. So in this talk, in the next slides, I will try to convince you that it is very powerful to extend the application of very standard but yet simple and common analysis methods usually used in the investigation of wave dynamics in single magnetic structure, and to extend them to the global scales of the sun. So to cover the global scales typical of the solar activity cycle. So we want to bridge this gap and to use the small scale magnetic elements to gain information about the global dynamics of the sun. And I will try to convince how this is a powerful methodology, which is enabled now by observations covering a solar activity cycle, like those provided by HMI on board the Solar Dynamics Observatory. So at least, of course, we want to cover, we cover at least those scales, the typical scales of the sun, which we can cover, of course. Of course, there are also longer time scales, which are not able, which we are not able to investigate. But already covering a solar activity cycle can provide really unexpected results and can provide really a new perspective. So what we want to do is to bridge, to investigate a possible connection between the small spatial scales and the global scales of the solar, of the stellar structure. And to do so, we take advantage of stable and long observations from the Solar Dynamics Observatory, HMI, spanning the period from 2011 to 2022, so 11 years. And we investigate the dynamics of small-scale magnetic elements continuously for 11 years. Actually, we cover, we focus on a small patch, a disk center, as illustrated here, a small patch 400 by 400 arc seconds, a disk center to avoid projection effects. And we track magnetic elements in windows of 40 minutes every 3 days, continuously for 11 years. This is, at the end of the day, we have tracked 31 million magnetic elements. And this is a magnetic map showing an example of magnetic elements that we have collected and identified. So this is an example of identification. So each magnetic element is labeled, and it is tracked over its entire lifetime. And so that from this tracking, we have we obtain the position of the magnetic element in time, and from that we can obtain the velocity, horizontal velocity, and of course also the horizontal velocity oscillations, which we are interested in. For the entire 31 million magnetic elements set. So this is done continuously, of course, and this provides the most comprehensive statistical analysis of this kind today. The cadence of the data is 45 seconds. So this allows us to investigate also at the same time, also the typical periodicities of these magnetic structures. As I said before, the typical periods of the kink modes for these magnetic structures are of the order of between 2 and 10 milliyears. So at the same time, we are exploring these timescales, but also the timescales typical of the solar activity. So in such a way to bridge the gap between these two temporal scales. And this is just to provide you the context about the statistical sample that we have investigated. Again, this is an example of magnetic map with these magnetic elements. And of course, these are advected by the turbulent convection, so we can follow them in time using a very simple and standard tracking methodology, which is generally used in typically for the investigation of the same physical processes, but on short data sets. So this is exactly the same analysis you can find in the literature in many works, which is applied over longer timescales, much longer timescales. So it is nothing new from the point of view of the methodology employed, from the point of view of the analysis performed, but we are simply applying the same analysis to the longer timescales, and this is obtained thanks to the availability of long duration data coverage, as in the case of HMI. So just to provide you some context information, this is the probability density function, so the distribution of the effective radius of these magnetic structures that we have identified and tracked. This is this is obtained from the 31 million magnetic elements. As you can see, we have an effective radius of the order of 300 kilometers. This is an effective radius. So if the magnetic structure is elongated, the shape is assumed to be circular. So that's the reason why the peak of this distribution is below the spatial resolution of the instrument. And on the bottom panel, you also can see the distribution of the magnetic field, and the peak is of the order the main peak is at around 60 Gauss. So these are very small scale magnetic elements, and are very close to the resolution limit of the instrument, which is 1 arcsecond in terms of spatial scales, but also very close to the sensitivity of the instrument itself. And again, we do so, we perform this analysis covering from 2011 to 2022. So as you can see here in this plot, I'm sorry, I cannot use the pointer, but you can see in the bottom panel the sunspot number, providing some reference for the solar activity. So you can see that we are spanning one activity cycle from one minimum to another minimum. Actually, we also capture the rise of the next maximum, the same one that we are witnessing now. And this is just to provide you some context. So we do this high resolution data analysis for the entire solar cycle, and we have collected 31 million magnetic elements to do so. So what we, as I said before, what we are doing is tracking each magnetic element, and for each magnetic element, we have the horizontal displacement, which is the result of the granular convection, essentially. And in addition, we also have the velocity perturbations, so the horizontal velocity perturbations, which represent from which we extract information about the kink oscillations of these flux tubes. This is some result from this analysis. In the purple and bluish plot on the upper right panel, you see the amplitude of the oscillations of these magnetic elements. So generally speaking, we in the literature, you see that these magnetic elements have a velocity amplitude of the order of 1-2 kilometers per second. By exploiting the number of elements that we are collecting and analyzing at the same time, here we are able actually to really give a number, and the amplitude of oscillations of these magnetic elements, of the kink oscillations of these magnetic elements, is between 1.3 and 1.5. So we are really giving constraints about the velocity amplitudes of these magnetic elements, and this is thanks to the statistics. But at the same time, what we noticed from the very first time was a slight difference between the amplitude of oscillation in the north-south direction and the oscillation in the east-west direction. So again, in the upper right panel, you see the amplitude of oscillation as a function of time, so spanning from the 2011 to 2022 in the east-west direction, so parallel to the equator of the sun, and in the north-south direction. The bluish dots are in the north-south direction. As you can see, in the north-south direction, the amplitude of oscillations of these magnetic elements is slightly more smaller. And this difference can be better seen in the bottom right panel, where we plot the velocity difference. So the difference between the amplitude of oscillations of the oscillations in the X direction and in the Y direction. As you can see again in the X direction, so parallel to the equator, to the rotation of the sun, we see that there is an increase of the amplitude. So these waves are actually polarized, and there is an increase of amplitude in the again in the east-west direction, so parallel to the rotation, with respect to the amplitude of horizontal oscillations in the north-south direction. And this polarization is also modulated by the solar cycle. As you can see, there is a peak around 2015, 2016, which is slightly lagging behind the peak that we can see in the solar activity cycle, which is represented by the sunspot number. So this is slightly, this peak, this polarization of the kink oscillations is slightly lagging behind the solar activity peak. So again, this is something that is not possible to be seen by only focusing on short duration data sets of the order of course, a couple of hours, for example, but you really need to expand your analysis, to extend your analysis to the longer time scales. And this is also suggesting that the small scales are actually linked to the global scales in some way. Again, this is another visualization showing how this slight difference. So the velocity amplitude in the direction parallel to the equator during the solar maximum is this amplitude of oscillation is larger with respect to the amplitude of oscillation in the north-south direction. So for the same magnetic elements, statistically, this is something which is obtained from a statistical point of view, we see this slight difference of the order of less than 0.1 kilometers per second. During the solar minimum, the amplitude of oscillation of these oscillations in the X and Y direction is partially overlapped. So as you can see in the bottom panel, this is the difference is reduced, and the difference is minimum. While when we approach the solar maximum, this difference becomes larger and larger. But actually, the maximum difference is obtained just after the peak of the solar activity is likely.
Can I interrupt with a?
Yes, sure.
Now, at solar maximum, I mean, you show a picture of the supergranular network
Yeah.
Now, isn't it true that solar maximum, even the small scale flux elements be more densely packed?
Yes.
So
yes.
It'd be useful. I mean, maybe you're going to show a comparison with the
yes.
Yeah.
Yeah, this
Okay.
is actually something we are investigating at this moment. Of course, this is something that we have to take into account. There is a difference, an intrinsic difference in the magnetic fields due to the presence of larger scale magnetic fields during the maximum, of course.
So, I mean, if at maximum the flux tubes are more densely packed, there
Yes.
might be a different systematic difference in like things like orientation of the flux tubes, things like that, that need to be taken into account. But
Yeah. From the preliminary results we are obtaining, it doesn't seem to be the final answer to this problem. But of course, this has to be really considered and taken into account very carefully. Of course, yeah, you're right.
and also, I mean, sometimes don't you have like a active region plage or something in your field of view? I mean, I would expect large differences between your measurements in the plage and in the quiet regions. And
Yes, yes. Even if in terms of sizes, for example, and magnetic flux, we have checked that the population I mean, we are collecting more or less the same features in terms of size and magnetic flux. But of course, from the dynamic point of view, it is also important to consider the environment. As you say, the plage or the network, or if they are close to an active region, of course.
yeah, I mean, in the plage, it's well known that the supergranulation is suppressed, and the motions are suppressed.
Yes, yes. But again, focusing on this this feature, so the fact that we observe the peak of this velocity difference slightly lagging behind the peak of the solar activity, we have tried to just to provide some explanation, some possible explanation. This is, of course, speculation. We don't have enough information to constrain and to really point to a particular explanation for that. But we took dynamo simulations, and we have integrated the same latitudes that we are exploring in the observations. We have estimated the velocity perturbation at the photospheric layers of the rotational velocity. And as you can see here in this, in the bottom right panel, this is the black curve is the solar activity, and the red curve is the torsional, represents the torsional oscillations. So global torsional oscillations, as you can see, which are due to the Lorentz force. And this is, as you can see, also in this case, this is from the simulations, dynamo simulations. You can see that the peak is lagging behind this the solar activity. Therefore, one possible interpretation. So this is suggesting in some way that there might be some link to the torsional oscillations that are expected in the stellar structure. Although there is some problem also in this case, because we are not able to explain why this perturbations in the rotational velocity are actually approaching the heights of the photospheric layers that we are exploring with our data. So this is another problem. So this is a possible, just to provide, to put forward some possible explanation for this velocity difference and this polarization of the kink oscillations in these small-scale magnetic elements. But independently of the real cause of this velocity difference. So we can say that the small scales, there is a coupling between the small scales and the global scales of the sun. So, and the coupling is particularly evident when you see that there is a modulation of this velocity difference with the solar cycle. So in some way, the small scales are actually coupled to the global scales. And this is against the general assumption that we generally used in our in the investigations of this kind of in the dynamics, in the wave dynamics of small-scale magnetic elements. And the assumption is generally that the waves are excited by local processes. But our results are pointing to a new paradigm where the local oscillation, the small-scale behavior of the small-scale magnetic elements is also dominated by some global scale driver. But there are other unexpected results. As you can see here, from this velocity perturbations, we have also estimated the main frequencies involved. So you all know that the photosphere is dominated by 3 milliars, so 5-minute oscillations. This is the dominant period due to the P modes. So the general picture is that these P modes are absorbed by the magnetic fields and are converted to MHD modes inside the magnetic fields and so on. So we expect that the magnetic fields in the solar photosphere are also dominated by this frequency. But this is not the case. So by using the large number of magnetic elements, we could be able to investigate the dominant frequencies of these kink oscillations that we identify in this small-scale magnetic elements. And surprisingly, the main dominant frequency is not 3 milliars, but it is 5 milliars, which is generally chromospheric frequency. So we identify chromospheric frequency in a photospheric environment. This is something that we are not able at this time to explain. But I can tell you that this dominant frequency is also found in sunspots. So sunspots are also not only dominated by 3 milliars, so the main period of the P modes, so the main period that is expected, but also by additional frequencies of the order of 5 milliars. And this is another paper that we have published recently showing that these frequencies were found in a sample of active regions where we investigated a number of active regions of the order of 1,000 active regions in total. So this is another unexpected information, unexpected result. And in this case, in this plot, in the upper right plot, you see the distribution of frequencies. So each column in the plot, in the orange plot, is a distribution which is obtained over 2 weeks as a function of time. So every 2 weeks, we produce a distribution of the probability density function of the frequencies of these kink oscillations. And we did this as a function of time for the entire solar cycle. As you can see again, there is the average, the dominant frequency is not 3 milliars, it's 5 milliars. And in addition to this, there is also a modulation of the amplitude of these oscillations. So when the solar cycle reaches its maximum, we have an increased amplitude of these oscillations. And again, I would like to stress the fact that this is really unexpected frequency, because generally these frequencies are found in the chromosphere. Due to the cutoff frequency, the atmosphere acts as a filter for the low frequencies, and the only frequencies which are able to upward propagate are the frequencies above the cutoff frequency, which is close to 5 milliamps. So generally we observe and we expect to see these frequencies in the chromosphere, in the chromospheric layers, but surprisingly we detected these frequencies in the photosphere and in the kink oscillations, so in the horizontal displacement of these flux tubes. Or this, of course, this again, these flux tubes, of course, may have different natures during the solar cycle. So due to the magnetic flux, due to the emergence of active regions, the solar maximum, of course, the nature of this magnetic elements can be slightly different, as we were saying before. But again, the frequency is more or less the same all over the across the solar cycle. Conclusions: we have investigated the dynamics of the wave dynamics of 31 million magnetic elements, which were tracked at this center, covering an entire solar cycle. And this was done to bridge the gap between the small scales and the global scales of the sun, so to see whether there is a cross-coupling between the different scales. What we have found is that the horizontal perturbations of these photospheric magnetic elements is not only driven by local plasma processes. And this was, as I was saying before, this is the general assumption, right? We generally assume that the waves which are driven, excited within these magnetic elements are actually driven by local plasma processes. So, for example, convection, turbulent convection, buffeting, and so on. But our results are also showing that there is probably an additional driver acting on longer timescales. And this is this is also showing a possible link between the global and the small scales. Of course, the sun is a complex system, and cross-scale coupling is not surprising in complex systems. So while this is not surprising, the real the cause of this possible coupling between so different time scales and spatial scales is yet in more detail. And as I was saying before, there is some indication that this can be due to global torsional oscillations. And this was done using, at the same time, dynamo simulations. Although there are still problems, and one of the problems is that it is not expected that these torsional oscillations can really touch the photospheric layers, so that these magnetic fields can really be influenced by these torsional oscillations, unless these magnetic elements are actually rooted well deep, much deeper than we thought before, so that they can really sense this kind of torsional oscillations. And what we are observing is actually the result of this additional driver, in addition to the local driver due to the granular buffeting and the granular convection. So as I said, one possibility is the effect of the dynamo torsional oscillations, although this is not, it is too early to draw conclusions. But this is possibly one of the mechanisms involved. And also, we also have found unexpected frequencies, in particular a 5 millihertz frequency, dominant frequency for these oscillations. And as I said before, this is part of a series of works we are doing using the same data, actually. So this frequency is also now found in photospheric sunspots. So this is not only linked to the small-scale magnetic elements, but also to the larger magnetic structures. But something that I would like to underline in this case is that if you remember the distribution of sizes of magnetic flux for these magnetic elements, it's quite broad. So in case of resonant modes, we would expect one particular frequency for each magnetic element because each magnetic element is different from the others. So we would expect, like in a guitar string, a particular dominant frequency for each magnetic element. But this is not the case. So even if we have a broad distribution of magnetic elements collected and investigated, we find a particular single frequency. This is suggesting that this frequency is possibly not really linked to the magnetic elements themselves, but actually to the driver. So this is probably due to the driver, which is exciting these oscillations. This is not a resonant frequency. What I would like to say is that this is not a resonant frequency probably of the magnetic structures, because the magnetic structures are very different from each other. And this is also the case of the sunspots. We have in this new paper, which I'm referring to in this slide, a recent paper by one of my students, Michele Berretti. As you can see that these frequencies are actually found in a very broad range of different active regions, suggesting that these frequencies are actually linked to the driver. And finally, let me, okay, this is what I was saying. So the sample is very not homogeneous in terms of shapes, magnetic flux and size. So but still we observe one particular frequency, even in this case. And finally, let me conclude with something that I don't think I have to convince you that SDO and HMI are really offering an unprecedented opportunity to frame, to put in a broader context the small-scale dynamics of small-scale magnetic elements. So they are offering really an unprecedented opportunity to investigate the dynamics of small-scale magnetic elements, and to frame these investigations in the broader context of the global scale of the sun. So really the main timescales of our star. And this is really, and I think it is very important it is these are very useful data and very useful mission. And it's becoming more and more useful when as time goes by, because we are collecting more and more data. So we are exploring, we are covering a larger fraction of the solar activity cycle. So they are becoming more and more important. And I would like to conclude my talk by underlining this aspect. But I'm sure that I don't have to convince about this, about the importance of this kind of missions. And so thank you very much again for your attention, and I'm here for your questions and ready for discussing this. If you have ideas also to provide this, are very welcome. Thank you very much.
Thank you, Marco. There are already a few questions and discussion in the chats. I meant to interrupt and ask you, but soon you are already in the conclusion slide, so I hold them. There are at least 3 questions in the chats already. The first one
Or
from
maybe I can open the chat. Sorry.
Oh, I meant to let them
okay.
ask you directly. Don't worry about the slide, the chats. So first one by Vigo. Vigo, do you want to
Sure.
ask directly?
Yeah, I can ask directly. I was just curious. This may be a red herring, but I was curious. How large is the change in differential rotation across your field of view? I mean, from the middle until the edges. That was in connection with the the different velocities you find in parallel and perpendicular to the rotation axis.
Yeah, good question. Maybe I didn't stress this point. You mean the I cannot change the slides. Oh, this is okay. No, this is the okay. You mean this one? You see,
Yes.
the red curve here is the velocity perturbation of the torsional rotation, which is estimated by considering exactly the same range of latitudes that we are considering in our investigation. As a function of the latitude, there is quite a big difference, but in this particular case, we are estimating the torsional, the perturbation at the same latitudes that we are considering in our investigation. So this is just to compare these simulations with our results.
Okay. Next question from Sushant.
Hi, this is Sushant. So, looking at the, can you hear me?
Yes, I can.
Yes.
Looking at the plot on the bottom left, the red dots, the velocity difference, which kind of it measures torsional oscillation. The velocities you find seem to be 100 to 150 meters per second, whereas torsional oscillation, as reported by helioseismic and other feature tracking methods, is less than 5 meters per second. So I was wondering what makes you confident that what you're seeing is torsional oscillation.
You mean the red dots here?
Yeah. Yeah.
Yeah, this is, of course, this is this is an open point in our opinion. I mean, we don't really have a clear say a convincing hypothesis about the source of this difference. But what I can tell you is that each point in this case is the peak of the distribution, a statistical distribution. So for each peak, for each point, we have a distribution of velocities. So that may explain why this is slightly smaller than expected.
It's actually larger. It's 20 times larger than expected.
Okay.
But what is it with respect to? Like, it's a velocity difference, right? So what has been subtracted from this?
This is just perturbations with respect to the background velocity. So this is the RMS of the horizontal oscillations after removing the average.
Oh, okay, this is RMS. So this is the thickness of the distribution. Okay, that makes sense. Okay, thanks.
Okay. Amy also have a question, and then we have 2 more hands raised. Amy, go first.
Hi, thanks for such a nice seminar. It's been really great to see this. Can you go back to
Okay.
the very beginning and show which of the visualizations of the modes, what you're measuring most represents?
This one?
This one.
Yes.
So in terms of the amplitudes of what you're measuring and the size of the flux tube, we're seeing deformations as well as displacement of the tube. Is that right?
You mean in this case, we have, you also see longitudinal velocity, right?
Well, that's what I'm
This is
trying
what you
to
mean.
visualize. You're giving the amplitude of the oscillation in terms of a velocity, and then we have a
Yes.
thickness of the tube. And so the velocity is, I'm trying to just visualize it. So this tube is not waving around like the image you showed of the data.
You mean that, of course, these flux tubes are advected by the granular convection. So, and on top of that, there is a displacement, a longer term displacement. And on top of that, there are also oscillations. This is what you mean?
I guess
get
I'm
your
just having a
point?
hard time visualizing what this kink mode looks like.
Maybe this is better. You see that there is a periodic displacement of the flux tube. And what we observe is that we have a preferential direction. In the east-west direction, the amplitude of this oscillation is slightly larger than in the other direction.
So the amplitude and velocity was something like 1.4 kilometers per second. Was that right?
Yes,
And
yes,
the period is 180 seconds.
yes.
So that displacement is that larger than
Well,
the flux tube itself?
no, okay. Not always, maybe for the smallest ones. But what we did is we take the body center of the flux tube. So we can also, using, I mean, the body center, we can also detect very small oscillations.
Okay, thank you.
Okay, Sasha and then Kevin. Sasha, do you have a question?
Yes. Thank you for a very interesting talk. And I just posted a link to our paper. We did very similar study with Junwei Zhao and Tom Duval using high resolution MDI data. MDI had a high resolution field of view, which is the same resolution as HMI. And also we studied variations with solar cycle rotational velocities. And the results are very similar, I believe, in terms of rotation velocity. Our interpretation was in terms of subsurface shear layer, because deeper layers, if magnetic elements, larger magnetic elements are rooted deeper, then they rotate faster, and that probably happens with solar cycle. And also we investigated, it's important to look at the connection to the magnetic field strength. So I believe that in our paper we also investigated. It's only 5 years of MDI, and we didn't continue after this, but you're probably not familiar with this paper that I posted on chat.
Yes. Thank you very much. Thank you very much
Thank you
for your comment. Thank you.
Kevin?
Thanks. Thanks, Marco.
Hi, Kevin.
Very interesting. Ciao. So I guess this is maybe related to Vigo's question, but so you tracked the HMI images rigidly to take out the solar rotation, right? Before you did the
Sorry, say that
Swami
again,
feature.
please. Sorry.
The images were co-aligned to take out
Yes,
the
of
bulk
course.
solar rotation.
Yes.
But they
yes.
span plus or minus 10 degrees in latitude, maybe more depending on the B angle. So there's some differential rotation within your box.
Yeah.
And so that may introduce different, and if the features have different distributions with the cycle, that could
Okay.
introduce a different weighting of the rotational velocities.
Yeah. Okay. First of all, I underline that this is not the case during the solar minimum, but still you should have this kind of effect. So we only see this difference. I mean, this difference becomes larger at the solar maximum, indicating that there is no differential rotation, I should say, because otherwise we would also see the same during the solar minimum. And also, in addition to this, for each individual magnetic element, we removed the average, the background velocity. So we are only looking at the perturbations with respect to the background velocity. So in this way, we remove this we get rid of this effect.
Okay. Mm-hmm. So for each feature,
even if in the case this was not a perfect removal, if it was true, we would have expected the same behavior also the solar minimum, but this is not the case.
Yeah, I was just thinking there could be different distributions of features.
Yes,
maybe. So the 1.4 kilometers a second average is after you've taken out any flows.
Yes.
Or the constant motion of that feature. Okay, so the flows have been taken out. The drift, some of the drift from the granular.
Yeah.
Pushing. Okay. Thanks.
You're welcome.
Okay, that's all the hands raised. Is there any
may
last
I?
question? Yes,
Yeah,
sure.
yeah. I'm sorry. I must have an old version of Zoom. I don't see any way to raise my hand. This is David Hathaway here. This is a fascinating study. I really liked it. The fact that you see the oscillations of these flux tubes at 5 millihertz, which is a chromospheric oscillation, fits in with, well, they're driving chromospheric oscillations. The big mystery to me is why they are oscillating at 5 millihertz when they are embedded in a photospheric plasma that is surrounded by waves that are at, I'm sorry, yeah, at 3 millihertz.
Yes.
And again, another side comment, although it's related, that I would think that they are moved around by local processes all the time. Those processes may change with the solar cycle, but the mystery to me is that I would have thought 3 millihertz, not 5. So it's
this is also the mystery to me.
Yeah.
Yes. Well, this is also a mystery to me. But if you remember papers in the 80s by our Russian colleagues, remember Zugzda and colleagues, for example, they talked about a possible photospheric cavity with similar frequencies. So our problem is how to prove this with the data we have. Of course, the reality is much more complicated. So, but in my opinion, this could be also a possibility to be explored.
Again, very, very nice. Thanks so much.
Actually, that was this oscillations were studied in several petrolines by Stuart Jeffries. Traveled to South Pole to do these observations. So, particularly studied what and interpretations in terms of acoustic cut of frequency. As far as I know, that was this oscillation. But there are data on several heights, and also at Gregory telescope they had a specific instrument to observe these oscillations, how they propagate.
Yes. Yeah, they use the MOF observations at 2
in
heights.
addition to HMI, we need some other data to understand this.
Yeah, but for the kink waves, the cutoff frequency is very small, right?
5 millihertz is not kink. It's probably acoustic, magnetoacoustic.
Yeah.
Okay, that seems to be the last question. Last chance if someone else has another question.
I have one more comment. This is
okay.
The small scale flux seems to have two independent sources. One is the active regions, the large, emerging active regions. And then when they break up, they become part of the small scale field. But then there's another source. People talk about surface dynamo or what, and that is also responsible for small scale flux. That includes probably ephemeral regions and so on. And those two sources could be rooted at different depths.
Yes.
So
Yeah.
I mean, I noticed that you don't make you just consider small scale flux in general. But I think you were talking about waves, so not the flux itself. So that might be okay. I don't know.
Yeah, no, good point. Of course. This is in line with what we were discussing before. Yes, of course, they can be rooted, maybe rooted at different layers, but still the frequency is the same, and this is really puzzling.
Okay, we are a little bit over time, and so let's thanks to our speaker again, and thank you everyone for attending, and especially the good discussions. As normal, we will put the recording online, and if someone wants to watch the recording again, or if you have missed any part, feel free to check our website later. So hope to see you all next month at our next seminar. Thank you, Marco, again.
Thank you very much for your invitation and for the discussions. They're useful. Thank you.
Thank you especially for staying late. This is we took your dinner time.
No problem.
Thank
No
you for
problem.
doing our time zone. Thank you.
Bye.
So hope to see you all next month. Bye.
Bye.